certificates now in program analysis, algorithms, generics, and metaprogramming and systems. And he has received several awards, including NSF Career Award and a few European Research Council grants, the ERC grants. And he has also received a lot of Best Paper Awards in several conferences like UPSLA, ISTA, ECOOP, and so on. He is also the co-founder of DDAUP, which is the company for smart contract security. And today he's going to tell us how ideas from context-sensitive static analysis led to the best smart contract decompiler. Yannis, the floor is yours.
Thank you very much, Devashmita. Can you hear me okay with the mic? Is it on at all? Okay, well, doesn't matter. We'll figure it out. So yeah, I'm Yannis. I'm from the University of Athens and co-founded DDAUP. So most of my time these days is spent at the company, and but also on research at the university. And this is very much joint academic industry work. It's joint work with a lot of people. The primary people for what I'm going to talk about today are the three people mentioned there, especially Neville Gregg, my co-founder, and the person who started the Decompiler, and Sifis, who's my PhD student, who has been evolving the Decompiler for the past few years. He just graduated. So we're talking about an actual tool with actual users. That's a snapshot of activity from a couple of days ago, but even if we sample it now, it's not going to be too different from that. So a few tens of users in the past half hour or in the last 5 minutes, and from all over the world. Basically, the context of this is we have built this long running public decompiler for EVM smart contracts, and I'll explain what EVM smart contracts are. It's called GigaHorse. It's now in version 3. So it's 3 very different incarnations of the decompiler, and you will see the evolution, or you will see some of the algorithms for version 2 and version 3. Everything that I do, if people know anything about me, probably for the past 20 years, they know that I've been doing static analysis declaratively. So we write logical rules in data log, and that's how we express the algorithms. But the same algorithms could be expressed any way you want. It's just that Datalog is very convenient for experimentation, and we actually get extremely good performance out of it as well, so we really love it. So the Decompiler has been much of the technology behind DDAUP, which is a general security company for smart contracts. It's used by many hundreds every day. We have 12,000 registered users. We started requiring registration a couple of years ago, and for the size of the space, it's a pretty large number. Pretty much all serious developers in the space use our tools. And we have documented all the progress in research publications, and I'll refer to them in more detail soon. The Decompiler is open source up to 3 address code, up to the IR, and only the very last step that produces something that looks like a high-level language instead of an IR is not open source. But that step is not so hard to actually replace. And if you want the results for a particular contract, you just come to our free site, and you get it anyway. It has everything you need for 8 different blockchains already decompiled. So that's the background. So let's now go even deeper. So programmable blockchains. Who's familiar with blockchains, first of all? Easy question, but not everyone is raising their hands. So a blockchain is like a database that's not stored anywhere. We call it a decentralized ledger. It's a replicated log of transactions that are grouped into blocks. They're secured by cryptography. So you can be sure that everyone, after a very short period of time, they have exactly the same view of the data without the data being held in any trusted place. It's just replicated in maybe thousands of different places. In the case of Ethereum, close to 10,000 nodes are actually the most active participants of the network. And they all hold the same data, and new transactions come in all the time. And this chain of blocks that contain transactions, it always gets expanded. So this started with Bitcoin. So long time ago, was it 2008, I think, or something? So it started with Bitcoin. a while ago. It had the main data structures for a blockchain, and a little over 10 years ago, Ethereum came in and added programmability. The idea for Ethereum was that if we have a memory that 10,000 different parties share and they all agree on, why do we use this memory just to keep transactions with amounts, etc.? Why don't we use it as a proper computer memory? Install programs, run programs over that memory, have the memory hold the actual data of the programs. So the blockchain has become a huge virtual machine that runs millions of different programs. Of course, most of the time, those programs are idle. They wait for a transaction to come in and tell them, execute function foo with this input, and then the program executes. And everyone who participates in the network replicates exactly the same logic, or at least validates that that logic of the program was executed correctly as reflected on the data. These programs are called smart contracts. So programmable blockchains have smart contracts. It's just a name. It's not a contract in any way. It's just a name for programs, smart contracts. So don't assign any semantics to it. And smart contracts are typically written in Solidity, at least in EVM blockchains. So Solidity is the high-level language. It's an imperative language that's a cross between, let's say, JavaScript. It's like a typed JavaScript-based language, but with special facilities that deal with the blockchain state. So it's actually a fairly convenient language, but obviously with lots of blind spots that lead to insecurities. Now, overall, if you're here, probably you're doing static analysis, and I want to emphasize that the domain of smart contracts is an ideal domain for application of all sorts of program analysis and verification techniques. And in fact, many people from the analysis community have transitioned to that domain, and they apply their techniques there with several leading companies that have been founded by PL researchers. Obviously, the reason for that is that it's a domain where correctness is crucial. We have to have correct contracts, correct programs, because they manage funds right away. We're talking about a blockchain that produces a cryptocurrency. The program itself handles money. You find a vulnerability, you can steal large amounts typically. So correctness is crucial, and then this is an ideal domain to apply research, because unlike any past analysis work that I've personally done, like on LLVM, on the Java VM, here we have all the code public, all the past executions public, the current state public. I can analyze programs, and I can get their code. I can get everything that they've done in the past. I can get the current state of their heap. And that's not something that you can do for publicly deployed programs, even open source programs, on nearly any other domain. So it's an ideal domain for applying these techniques, and it has a great need for program analysis techniques. So after this advertisement, let's try to dig a little deeper. The specific context of what I'm going to discuss is a subset of the blockchains, of the programmable blockchains, but it's the largest subset. So 80 to 90% of the value of programmable blockchains is in blockchains that, as a virtual machine, they have what's called the Ethereum virtual machine. That was pioneered by Ethereum and has been adopted by other compatible blockchains. So such blockchains are Ethereum, obviously, Binance Base, Optimism, Arbitrum, Avalanche C-Chain, ZK Sync, Polygon. So lots of major value blockchains use the same VM for executing contracts. There are non-EVM blockchains, of course, and you may have heard of them. I mean, there's Aptos and Sui, Cardano, Solana, Canton. These are probably the major ones that are programmable, but they don't use the EVM. So we're talking, everything in this talk is going to be EVM-based blockchains. And the EVM, the Ethereum VM, is a simple, low-level virtual machine. It's designed to be easily implemented. It's not designed to allow reverse engineering of contracts or analysis or anything like that. We will see it's actually pretty hostile to that, and that's why we need a decompiler. OK, so what's decompilation? Let's try to get a mental picture for what we are really trying to do here. Like I said, the Ethereum VM is an extremely low-level VM. So what does that mean? think of any IR or assembly you know, and this is probably lower level. It's lower level than x86 assembly in many respects. In a couple of respects, it's a little higher level, but in many respects, it's low level. It has no type information, has one data type, which is 256-bit integers. Everything else is done with masking. It has no abstraction of functions at all. We don't know functions. The good thing is that we know the beginning of basic blocks. That's the only good thing. We don't know even dump instructions that implement an if, a switch, a while, a for, against dump instructions that implement a call or a return. All control flow is dump. This is like continuation passing style, if you are familiar with that. It's basically an execution that just goes forward. It just dumps. Dumps at whatever is at the top of the stack. And this dumping to whatever is at the top of the stack could be a function call, could be a function return. It could be an if, it could be a for, it could be the back edge for a for, it could be anything. But all control flow is dump, dump, dump. So it's extremely low-level control flow. And that's going to be the main problem that I will focus on today algorithmically. So the algorithms we're going to do, they all come out of this problem. The dump targets are dynamic. Like I said, you dump, you don't know what you're jumping to. It's whatever is at the top of the stack at that particular moment. If the stack has been rearranged by complex logic, whatever was left at the top is what you jump to when you get a jump instruction. So it's extremely low-level VM. And to make matters worse, there are very aggressive optimizations that compilers perform. If the compiler sees the same basic block used 5 different ways from 5 different functions, but it happens to be the same 4 low-level instructions, it's just going to jump to the same basic block from 5 different functions. It's going to reuse code aggressively. So we need to reverse engineer all of that to get a high-level view of the program, because lots of flows have been merged at the low level. OK, so this is an example smart contract. It's written in Solidity. The language that I said earlier is the dominant language for EVM smart contracts. So you get an idea. We have interfaces, much like interfaces in an OO language. We have contracts that are much like classes in an OO language, although we don't do too much instantiation. New is not too common, because every time you do new, it persistently registers a copy of that contract on the blockchain. So new is costly. We typically install the contract once. We rarely do new. I mean, there are a few facilities that do it. But otherwise, it's basically a standard static object-oriented language. We see functions. We see the syntax for functions there. We don't need too much of it. And at the down here, I say I have a function transfer with fee. It takes some parameters. It takes a couple of fee adjustments here. And then it does an actual transfer of funds of an amount that's equal to the amount passed in minus the default fee, which is a state variable. It's stored persistently on the blockchain, minus fee A, minus fee B, which are local variables here. And I say here that this line makes 3 private function calls. So this is part of what we will need to reverse engineer from the low-level code. Can you guess where the functions came in? Because this is not a private function call. This is a public function call, the transfer. It calls a function on an external contract. In this code, that single line, where do you think the 3 private function calls come from? Any theories? Yes? It's the minus signs. This is what we see 3 of. So every use of the minus operator in Solidity 0.8 and above, which has been the case for the past 2.5 years, all the minus operations, they jump to a function that's safe subtraction. And it checks that it doesn't underflow. If it underflows, it throws an exception. Solidity didn't used to have that, but now that's what it does. So here we actually have 3 function calls that we need to reverse engineer. They're the same function called 3 times in there. So much of the difficulty will be detecting those function calls, because like I said, these don't exist as function calls in the low-level code. They're just jumps. And we need to recognize, hey, this is a function here. And the code jumps to the same function from 3 different points. OK, so the contract gets compiled into bytecode like this. That's what gets installed on the blockchain in the shared memory of the blockchain. And that's what gets executed. If we decompile this, if we disassemble this, it looks like an assembly, much like a usual assembly. But you can see that it's a stack machine. All it has is pushes and pops and dupes, duplicate locations of the stack. But it's a stack machine. And then in this code, we will recognize some patterns that we will come to again and again. And I've pointed them out there on the right. And we'll get back to those patterns because they will be important for some of the points that I'd like to make. But basically, you see that all the patterns are doing something like manipulating the stack and eventually doing a conditional jump. That's jump I is jump if under a condition, or an unconditional jump. And we'll need to see what each one of those does and give them a meaning in different ways. OK, so what's decompilation in our setting? We use a decompiler as 2 things. First of all, for human comprehension of the code. That's why we have the 12,000 registered users in our service, because they come to do security analysis or to reverse engineer bots or whatever. They want to understand the code. But we also use it as a platform. It's a platform to write automated analysis on top of. So for us, decompilation is the discovery or the recovery of an intermediate representation, of a structured intermediate representation that has functions, it has ifs, it has all these nice things that we want from very low-level bytecode. And to give you an idea what this looks like, the IR for our decompiler, the 3 address code, looks like this. It's still low level, and we do lift it 1 level up, but that's completely stochastic, and LLMs actually can do a pretty good job at the very last step. But you can already see several high-level patterns. We've recognized functions and how many arguments they take, including function calls here that pass arguments to those functions. And here we have jumps that are internal control flow instead of function calls and returns. So we know if a jump is an if or a for. Or we can recover that very, very easily from this. But certainly, we're not confusing it with a call or return. So this is the structured representation. That's the output of the open source version of our decompiler. So that's decompilation for us. Now, we've recovered all interesting things that we've wanted. And this has great application value for us and for others. Obviously, I said humans want to use it for investigations. We also use it as a platform for our tools. And the tools have been pretty successful. Like, the tools have found vulnerabilities for for billions of vulnerable funds. So we've gotten $3 million just in bug bounties for vulnerabilities we've discovered on tools that run on the output of the decompiler. So this has been pretty good for us. And we have contracts with some major clients in the space, such as Blockade and Binance. And of course, we always get integrations in third-party tools. So it's a pretty successful product for something that's so niche and low level. OK, so let's get to the technical challenges now that we got a taste of what is the decompiler, what it does, and what's the setting in which it operates. So number 1 challenge, and the one I'm going to focus on most, is control flow. Secondary challenge will be functions. And I will skip most of the stuff about functions because it's pretty analogous in challenges. But control flow lets us illustrate much of what I want to say. We looked at this picture before. That's the disassembled code. So we see patterns in the disassembled code. I can already tell you what this top pattern, this top right pattern is. This top right pattern is the dispatch of a public function. When a transaction comes in from the outside world, it includes what's called the 4-byte selector of the public function. Those are the 4 bytes you see there, the 12E49406. So the transaction includes this in its data. And this is the key to decide the entry point inside the smart contract. So this is pretty standard. This is pretty formulaic. We can recognize this pretty well. We always can recognize the public function entry points pretty well. This middle basic block here, it does pushes of 2 constants and then a jump. So it jumps to 104, which is at the top of the stack, but it has left on the stack 4D. Can you guess what it does? Most likely what it does, anyway. When do we need to push something on the stack and then jump to a block? I'm sorry? It's a return address, exactly. So this is most likely a function call. This is a high confidence function call. We left a return address on the stack. We put another address on the stack. We jumped to it. We left a continuation more accurately, because there could be tail call optimization, so it could be not where to return to, but what's the next call after that. But it's a continuation anyway. So think of it as a return address. That's the simplest way. This is the best pattern we can hope for. That's almost undisputable evidence of a function call. And we can know actually that 4D is the address of a block and not a random constant, because the beginnings of blocks are labeled by the jump dest instruction. So this is actually the only help that we get from the EVM. Jump dest is the only thing in which this gives us a little bit of high-level information. We know the beginnings of basic blocks. How about the bottom basic block here? Can you tell me whether it's an if, a switch, a for, a function return, a call? You cannot, because that basic block on its own means nothing. It does some rearrangement of the stack, and then it jumps at whatever was at the top. So in fact, the answer to my question is yes. It can be an if, it can be a for, it can be a function return, or a function call. In fact, it could be all 4, 5, 6 different things inside the same smart contract, depending on how we got to this basic block. So that's the difficulty there. Those kinds of basic blocks are the big difficulty in recovering high-level information. OK, so the heart of the problem is that how we got there determines the semantics of the code. So the execution of the code determines the meaning of the code. So there are other complications that have to do with modeling the contents of the stack to recover how many arguments we pass, et cetera. But we can stay at the very basic complication there. We don't know what's the control flow role of a basic block without knowing how we got there. So, and we can skip the function recovery. So the obvious first step is to say, if execution of the code determines the structure of the code, then just execute the code. So do some symbolic evaluation of the code, because you don't know what are the actual arguments. You don't know amounts. You don't know addresses. But you do know that the code, regardless of what amount or address was passed in, it will follow the same control flow. So why not use symbolic execution? And there are many decompilers that have started to do this, that have tried to do this, because it's the obvious thing. It's the easiest way to get a basic decompiler. And throughout the years, we've been running GigaHorse since 2018. And we had at least 3 different publications for the 3 different versions of GigaHorse. And every publication compares to a different decompiler. The old one compared to Porosity, which doesn't even exist anymore, pretty much. The other 2 still exist, Panoramix and Heimdall-RS, but they get updated. The state of the art for other decompilers constantly gets updated, simply because this doesn't work. Symbolic execution does not work for the decompilation problem. So that's not what we do. Let's illustrate how it doesn't work. This is a subset of results that we will glance at later as well. Basically, here's from the latest paper we had, here's how much code we recover for a set of smart contracts. Here's how much code GigaHorse recovers versus Heimdall. And we measure things that have to exist in the code. They're undisputably in the code, like unique external calls. These are externally observable, and we deduplicate based on the selector. So Those things, if we found them, they definitely do exist. So Gigahorse finds 13,000, Heimdall finds 9,800. So this is a very incomplete solution. It basically fails to decompile most of the code. It fails to find ways to explore many interesting paths. And same or worse happens with events. Again, externally observable things that have to exist in the code, they're not recovered very well. So if you do symbolic execution, you will get great code, you have high confidence, but you will get very incomplete decompilation. You will get about 60% of the contract code decompiled, is the point. Okay, so we all know why this was. If you execute the code, you need to cover an exponential or even infinite number of paths, but certainly exponential for finite execution. And even though you're doing symbolic execution based only on the branches, on the targets for jumps, you still cannot do a very complete job. I'm not saying that this is hopeless. I'm saying it's not as easy as people might think, and several people have tried it in the past and have failed. I mean, it's certainly the case that someone could do it in the future and get an amazing decompiler out of symbolic execution. But that's not what we do. So, and again, the difficulty can be illustrated by the complex fragment that we had there. We need to know exactly what's at the top of the stack. We need to follow all different paths that will get us there. So what we do instead is static analysis. And static analysis, as you probably know, is the approximation, the over-approximation typically of what the code does for all possible executions. And to get some precision, we use context sensitivity, which if you don't know exactly what it is, I will illustrate pretty shortly. So we classify all executions into a finite number of bins, pretty much. We don't do anything infinite or even exponential. It's actually polynomial. It's a polynomial, but pretty large number of bins. And we use the same algorithm for everything throughout the decompiler. What we get to execute every time, but also what's the current state of the stack, how many arguments this function gets, how many arguments are on the stack right now, how many return values come back, etc. OK, so pausing time, maybe it's not a bad time if there's any burning question before I continue. We're good.
Just curious, so
yeah.
What's the issue of adding a little bit more type information into the final binary?
A little bit more type information?
Yeah, just.
Well, first of all, if you don't know even the control flow of the program, it's pretty hard to add type information. Type information will typically be added right after we get the decompilation.
From the solidity, right? From the source language?
Oh, there's no issue. The issue is that the EVM is the EVM. The output, the bytecode has a specific form. It has specific vocabulary. It doesn't include types. And that's the only constant platform for these blockchains, the bytecode, which has not really changed. I mean, there have been additions of under 10 opcodes in 12 years or so that Ethereum has existed. There's some small additions, a couple of removals of instructions, but otherwise nothing much has changed in this bytecode. So the language of the VM has stayed constant, and that's what everyone can bet on, that this will be a constant, and they can build tools at that level. Because at the Solidity level, building tools is very, very hard. Solidity has had, every version has been incompatible with previous ones, and the next version is likely to be even less compatible than the previous ones. So it's a nightmare. You cannot build analysis tools on Solidity.
Is there a reason they designed it in this way, or is it just
Ease of execution of a VM. It's a very ease of building a VM, ease of implementation of a VM. It's a very simple language, so the VM is trivial to implement. OK. Yeah.
Just to brief, since you said that, like, why is that so important? I mean, sorry, why is ease of implementation?
It's not. It was.
We know how to implement, probably more complicated.
But that's what they chose back then, and it has stuck around, because now it's a platform, and it has tools, and it has lots of deployed code. So that's the answer. I mean, it could have been very different. It could have been a different IR. It could have been WASM. It could have been LLVM IR. It could have been something entirely different. It wasn't. So it brings its complications with that. The core of the problem is that we have a continuation passing style, very low-level VM, and we need to reverse engineer from that. But why it was done that way? It could have been done differently. It was done that way, though, and that's the status quo right now. OK, so now let's talk about context-sensitive static analysis, or the technical core of the work. Static analysis, you may know. If you don't, that's how I view it at least. It's a balancing of three elements: precision, completeness, and performance, or scalability. And we need to balance all those three at all times. And no algorithm is better just because it's better at precision, let's say. You take an algorithm and compare it to another on all three dimensions. And the way I present it is that static analysis is poetry. It's not prose. It's not trying to execute the program in full fidelity. It's trying to give you the right emotion about the program. It's trying to capture the right feelings about the program, at the right level of abstraction. OK, so let me try to illustrate in a couple of different ways. One of my favorite examples for static analysis, we have a program. It starts with y being 3, and depending on an external variable x, if it's not divisible by 2, it says y++. If it's not divisible by 4, it says y squared. And if you start with 3, your first reaction, and I know you're now reading the code and trying to execute it in your head, you're trying to see how many values of y can we see here. And the answer is we can have 3 values of y, 3, 9, or 16, because we cannot satisfy the first condition, but not the second one. If you're not divisible by 2, you're certainly not divisible by 4. But I bet you did not get to that conclusion in time. I bet you did not interpret that code in time quickly enough to figure out that the possible values of y are only these 3 and not 4, if you even got to the point of recognizing that there's 4. Now, the question is, if you have a static analysis and it tells you, oh, y, in this case, at the end of the program, can be 3, 9, 4, 16. Is it worse than a static analysis that tells you the fully precise answer, 3, 9, 16? And the answer is no. Of course it's not worse. It has worse precision, but it could be a much better analysis, because maybe to get to 3, 9, 16, you need to do a lot of symbolic reasoning, and you either become unscalable or incomplete. So you take a program analysis holistically on all 3 dimensions: precision, completeness, scalability. A static analysis that gives you this answer is over-approximate as well. It's just not fully precise, and it may actually be an excellent static analysis algorithm. It could be the right trade-off. So we are not always going for higher precision here. We're not executing the program. So to illustrate a different way, this is what I asked ChatGPT to produce as an example of poetry versus prose. And prose may say, the old man sat on the bench in the park. He watched as children played on the swings and slides. He smiled as he remembered his own childhood. Whereas static analysis will give you poetry. It will say, old man, children play, memories smile. We want to capture the feeling of the program. We are definitely abstracting away some details, but we want to capture the essence of the program. So if we want to get a little more precise, and this is probably the most important slide if you can manage to internalize it, if we're doing execution or model checking, we have per trace, meaning for current instruction, but also all past instructions, how we got there, a single value per variable. And variable here means, like model checking people use it, both local variables on the stack and global variables on the heap. Everything is a variable. Everything that can be mutated is a variable. So we have a single value per variable depending on how we got there. And we keep track of how we got there because we do concrete execution. In static analysis, we don't. In static analysis, in context-sensitive static analysis, we keep per context a monotonically growing set of values. So per variable again. So we may say variable x can have any of those 5 values, and variable y can have any of those 5 values. If they're correlated, If the value for x is correlated with the value of y, we may never know it unless we have encoded it in our concept of context. Because we qualify all these by context, we keep these sets as small as possible. And for the same context, we get a single set for x, single set for y. So we don't confuse the information for different contexts. But if we don't have full precision inside a certain context, we cannot do any more than that. We completely lose all the correlation. We don't have a trace. We don't have anything. So it's a set-based thing. It's based on sets that grow. And we get precision by assigning contexts. So it's not entirely intuitive that this is a good platform for a decompiler, right? So how is a decompiler a static analyzer? Decompilation tries to give you exact code. So we need precision. And here we're talking about something that's approximate. And it only gets precision by adding good context on top of that. But like I said earlier, the problem with decompilation in this setting is to be complete. That's what symbolic execution fails at. So this is a great fit for static analysis. So we get completeness by definition, and then we have to worry about precision by defining the right kind of context. So that's the philosophy behind our decompiler. We want to keep context a very short, evocative summary of the current execution, which of course may be mixed with other executions. We classify all of those in a polynomial number of bins, like I said. It could be confused, but by designing context correctly, it's not often confused. It's typically discriminated very, very well. And it keeps the essence of this execution versus others that are dissimilar. If it groups together executions, it groups together executions that do the same thing as far as control flow is concerned. That's the idea of what we're trying to do. OK, so we need context for sure, for very, very simple reasons. We cannot do it with a context-insensitive static analysis, but you probably already figured that out because we saw some abstract basic blocks. We could have a basic block, for instance, that just does a jump. And it's going to do completely different things depending on whether we got to this 0x1 basic block from A or from B. If we came from A, this may be a function call, or it could be whatever. But when we jump, we're going to return to AA. If we came from B, when we jump, we're going to return to BB. So we definitely need some concept of context inside our analysis to get anything good. And what I'm going to present next is how precise this context can get. Are we all good with a big picture? Everything so far? We're good. OK. OK, so we don't have to dwell on the actual formalism, but I want you to get a mental picture of what our implementation and our algorithms look like. We define concepts such as these. These are the heart of the decompiler. Concepts like block edge, like an edge between two basic blocks, block input and block output. This models the stack completely. So it says at the beginning of this basic block, analyzed under context C, the ith location of the stack holds variable v, where variable has a strange definition. It could be a variable, could be data that got defined inside a previous basic block, or it could be another stack location if things came externally. But this is all detail, and we're not going to follow it. We're just going to try to get the feeling of what our algorithms are specified as. So we model all the execution, all the control flow with block input and block output relations. All of those are context sensitive. They're qualified by a context. And then a context is basically a sequence of basic blocks. It's n different basic blocks for some value of n. So we start from nothing, and we build up context as we execute. And the algorithms look a bit like this. So they just connect with standard semantics. If I have a constant jump to a certain jump destination, and I am at a certain block, then I create an edge from the from block to the to block. And here we use a magic function merge, which you may have seen in past work. That's our name for a context constructor between when we have an edge in the call graph, or in this case, in the CFG, in the control flow graph. So merge basically says that this entire algorithm will be parameterized. I'm not going to tell you what the context is going to be. I'm just going to put a parameterization point there. And by giving different definitions of merge, you can change the algorithm completely. You can have completely different algorithmic behavior of this same skeleton of code by defining how the context changes at the interesting points of change. And all this definition of the context, how it changes, is hidden behind merge. So these are the main points that I wanted to get intuitively, because this looks very much like the actual implementation code. Of course, the implementation code in full, it's many hundreds of rules, and the full decompiler and platform is many thousands of rules, but the core is not too much more complex than this. It's a straightforward execution based on current state of the stack and what we see as jumps. OK, so I say here that our context in our algorithm will be n basic blocks. So several people here have done context-sensitive static analysis in other settings. So what do you expect this n to be typically? How many basic blocks are going to be in our context? Or not basic blocks. I mean, in the Java setting, for instance, our context will be either invocation instructions or abstract objects. But how big do you expect this n to be? 2, 3. Mano, you would agree, right? That would be realistic. So in this setting, in the decompilation setting, this n, we often set it to 50 or something, but the default for our decompiler is 20. So we're talking about a much more detailed context. That's why this is a good fit for something that needs precision. Because smart contracts are small enough programs, and the task we want to perform is local enough, it's very strangely interweaved control flow, but it's very local. So by keeping a very precise context, much longer than what you would expect if you analyze Java, Rust, C++, whatever, we get the actual properties that we want. And that's why the algorithms that you're going to see next are also a little different, because it's a very different algorithm when you have a context depth of 3 at the most versus 20. In 20, you can actually find interesting patterns in the context and prune context, for instance. So that's a preview of what we're going to see. OK, so very quickly in this part, probably I can skip for the most part, just to give you the basics, and then we can skip to the results. I'm going to next present the algorithm behind the second version of GigaHorse, GigaHorse V2, which we call ellipmoc, compile, reverse. And intuitively, you can think of it as saying, pick your friends selectively. And we'll see what that means. OK, so GigaHorse was introduced in 2018. There was already a need for a better decompiler by 2020, 2021. And this is what brought about GigaHorse V2, ellipmoc. And the main thing for ellipmoc was a new version of context sensitivity. So that's the main change in the algorithm. There were other changes. So we have more advanced function reconstruction. We also have a path-sensitive algorithm somewhere there. But the main thing by far was the different version of context sensitivity. So let's try to illustrate that, because it's also going to get us insights about what I mean by parameterizing the same algorithmic core with different context sensitivities and getting very different algorithms. So let's say, for the sake of illustration, even though realistically our context is 20, let's take a context depth of 2, and we have basic blocks that look like this. And if we've come here from 2 different paths, from A or B, like before, we come to one from 2 different paths, a context of depth 2 will look roughly like this. It will say, oh, I got to this instruction from A, or I got to this instruction from B. And if I got to this instruction from A, my stack contains AA. If I got here from B, my stack contains BB. Can everyone read these and connect to the code, like how we got to these contexts up here? Visual language is clear enough, right? OK, so the context right now has depth 1. We imagine that the execution, that the analysis started from these blocks. And now we go to depth 2, which is our maximum, and it remembers 2 previous blocks. So it says, I came from 1, and before that, we came from A, and these are the contents. And of course, you can tell right away we hit the problem of finite depth, because at the next step here, we forget everything. We forget the interesting distinction, which is whether we entered this sequence of basic blocks from A or from B, and we forget it because we have depth 2. So here we remember that we came from 2, and then before from 1, but they're the same for the 2 paths. So we confuse what are the contents of the stack. We confuse AA and BB. And we want to actually keep precision. So the algorithm for GigaHorse v2, for ellipmoc, is what you see here. And the main, perhaps the most important insight is that we have a part of the context that's sticky. It doesn't get changed. And that's the public entry point, how we got to this point of the code, from which public function we came in. Every transaction starts from invoking a public function on the contract. This we remember forever. So that's very useful information for distinguishing different executions, and we remember that forever. We don't replace that for a finite context. It doesn't get replaced by more recent data. So this is the fragment that we saw before, or roughly the fragment that we saw before, which basically says, I can always recognize public entry points, and every context I will have will keep a 4-byte value like this to remember how we entered to get to this point. When we entered from that point, and the previous 2 basic blocks were this and that, here's the contents of the stack. Think of the algorithm as doing something like this. And now for the private component, for the actual variable component, the one that we saw of depth 2, we try to heuristically recognize private function calls and returns. And this we cannot do with full confidence. But we try to over-approximate. We try to recognize maybe 3 times more calls and returns than are really calls and returns, because we have not gotten to the full decompilation yet. We don't know for sure that these are calls and returns. But we can look at jumps and say, this most likely is a call or a return. So those are the only elements of context that we keep. We don't keep other basic blocks that could be ifs and fors and switches. We keep just calls and returns. So this is pretty much the algorithm in high-level form of GigaHorse v2, of ellipmoc. So here we will try to recognize, for instance, I said this fragment is high confidence call. We will recognize that, and we will remember the 45 as our previous basic block, because it's an important basic block in discriminating executions. So in our example here, obviously this is a trivial example, so nearly any algorithm could do better, but effectively we remember how we entered, the 4-byte quantity, and then here we remember only the important basic blocks on the context. So when we get down here, actually, we don't remember that we came from 1 or from 2. We remember all the way back to A or B. We've heuristically over-approximated calls and returns, and we keep only those in the context. This very simple idea was GigaHorse v2. I mean, combination of 2 ideas. First, keep the public function entry point, and then here, discriminate, keep only your friends, the basic blocks that will help you discriminate executions. And those are the ones that look like calls and returns. And in this picture, only A and B. Is that clear enough? Yes?
You clarify what is the essence of this over-approximation, because sometimes we over-approximate because we join, and sometimes we over-approximate because we widen, we guess something, and it's a bit a heuristic. And is it a heuristic here that you are using to do your over-approximation, or is it just you joining all incoming edges?
I don't quite see the distinction between the 2 reasons to over-approximate, so we can look into that. But the reason this is over-approximate is that there are many patterns that are not local at all. So for instance, we may infer that this is an important basic block, even though on its own, is completely neutral. It just rearranges the stack and jumps. But how will we identify that this is an important basic block? We will have all sorts of other heuristics. Like this gets called by 3 different places that are reachable from different public functions, for instance. That's a very simple heuristic. So right away, I may know that this join point of multiple execution flows may be important. Okay. So I think that we have both kinds of over-approximation in your vocabulary, both because a location in the stack could have multiple values. So we have actually joined executions, and we have not kept enough precision, but also because we want to heuristically say, hey, I could not tell that this is important before, but based on other signs, I can tell that I better keep this. It could be the low-level way to express something important at the high level, such as a call or a return.
Yeah, makes sense. Thank you.
OK, so we saw a simple algorithm, and similarly, we have other algorithms for function reconstruction, but this was good enough. What I want to point out is something that many of you know because you've worked with context-sensitive static analysis. By having a more intelligent definition of context, by producing better poetry, so to speak, we can get all the good things. So we get better scalability. So GigaHorse v2 is much more scalable than v1. Like on tough contracts, we get many fewer timeouts with default settings. But we also get much, much better precision. So these are precision metrics, such as unstructured control flow. Lower is better. Ellipmock, which is GigaHorse v2, is the lower bar by a lot. So we get better precision, better scalability, and even better completeness. Of course, here, this is a comparison with other decompilers here. And we've already seen before that we are much better than symbolic execution-based decompilers in terms of how much code we recover. So the good context sensitivity helps in everything. And selecting the right kind of context can be tremendously beneficial in static analysis. So this lesson we will also see again in GigaHorse v3, in the third algorithm for decompilation. But it's very, very clear in GigaHorse v2 as well. So let me now illustrate our latest algorithm, just published in 2025. It's codenamed Shrinker. And again, primarily, it's a different definition of context for the same skeleton of the analysis. Exact same logical rules, we change the context. Reality is never that simple, right? There's always other changes, other sub-algorithms that get introduced. But the core is that simple. At the core, Shrinker is better than Ellipmock only because of a better definition of context sensitivity. So by 2025, we've had more complications, new ways to produce bytecode with different patterns, much more advanced compilers, all the private functions that I discussed at the beginning, like the save subtraction functions. So lots of stuff that we needed to recover. So GigaHorse version 3 primarily had a new context sensitivity algorithm, but it had also lots of other stuff. So let's try to see what's this new context sensitivity algorithm. What's the new inside? And now we'll see a similar problem as before, similar pattern as before, but with depth 4. So what we have here, simplistically, you can think of it as calls and returns, although it's not really necessarily calls and returns. So we may have come to this basic block from 2 different sources, from A and B, like before. And what may happen is that we get to a completely neutral jump back here after pushing return values. And then we have effectively 2 returns with the blue edges here. So here, I return to 4, and then I return to 5, because that's what got pushed here. So this is the normal flow. And of course, like before, we want to remember how we came into this whole bunch of blocks, this whole complex of blocks here, whether we came from A or B. If we use the straightforward algorithm of depth 4, what happens is that we have a chain of more than 4 interesting basic blocks. They could be an over-approximation of calls and returns. So here we've lost precision, again, like before. So if you want to think about it, here we've maintained full precision. We remember that we came from 3, which came from 2, which came from 1, which came from B, but that's the limit of our context depth. We don't remember 5 elements. So when we do the second return, this edge here, we forget that we came originally from B or from A. We remember the 3 most recent and the very most recent basic block, which is 4. Problem clear enough? How we lose precision in this scenario? Yeah. Okay. So great simplification of our algorithm, extreme simplification. When calling a function, do we need to remember where it was called from? Yes. Clearly useful context-sensitive information. When a function returns, do we need to remember anything about its being called and what happened internally? The answer is no. So that's the intuition for our algorithm. And the algorithm, the new part, is the boldface text here, which basically says, if we find a likely private return, a function return, we check if the next block is the continuation of a function call, and if so, we truncate the context to eliminate everything that happened between the call and the return. So let's illustrate this. The idea is that when we get down here, if we recognize this, if we manage to recognize this edge as a function return, we don't keep the most recent context elements. We will actually truncate everything that happened between the edge that was the function call that we matched to this return and the function return. In this case here, this edge eliminates that we came from 2. So the context gets truncated. We keep just 1 and A down here. We don't keep 2, 1, A, and then 3 on top of that. So we eagerly truncate the context by trying to match calls and returns. We try to recognize call-return patterns and use them to truncate the context. That's the algorithm for GigaHorse v3, essentially. That's the main new idea of this algorithm. Again, the complication is that both the recognition of calls and returns is over-approximate. So we cannot be 100% sure. But it's a good over-approximate heuristic, good enough to tell us how to manipulate the context. By doing this truncation here, by forgetting that we did this call and return, we have enough room in our context to remember all the old information, that before this call and return, we came from 1, which before that came from A. And then we do that again here, because that's a return for this call. So we can truncate again that we came from 1, and just remember what we got down here, that the source of this execution was A or B. The example is slightly simplified, but the essence is exactly what I just described. So any questions so far? No. Well, the point is, this is not rocket science, right? It's not extremely deep insights. It's straightforward insights, and the complication is coming up with the insight, but also executing it well, matching the calls and returns while the analysis takes place. Okay, and again, the impact of improved context sensitivity is tremendous, and we get much better scalability than previous versions of GigaHorse. V3 versus V2 has many fewer timeouts, even in the toughest contexts, in the toughest settings, and we get much better precision. So all precision metrics are lower for the gray bar, which is GigaHorse v3, and significantly lower with respect to all imprecision that one can define. So it's very, very good, and it's actually even more complete. We're not missing, again, lower is better here because these are metrics of incompleteness, missing control flow or IR blocks, and all metrics of incompleteness are also lower with a new algorithm. And of course, compared to external algorithms, we get the results that we saw before, that we are much more complete compared to symbolic execution-based decompilers. So the conclusion, again, is that by using this algorithm, we can get much better scalability and precision at the same time. By the way, quick caveat on scalability. When I show timeouts, these are timeouts with the default settings. If we change the settings, we can decompile everything. but it may need manual intervention. But with the default settings of context depth and how many stack locations we model, et cetera, this is what timeouts we get. OK, so I will be wrapping up. So just to give a little time, I will mostly skip this part. There are many other challenges in decompilation. We only saw one of 4 I've identified here. The second one, the recognizing function arguments, is very similar because it's, again, modeling the stack. But there's also modeling memory, which is a transient heap. It's a heap that only exists during transaction execution. And modeling storage, which is a persistent heap. It's the part of the program's heap that stays on the blockchain persistently. It's like the file system of smart contracts. And we've done a lot of work on that. There's a lot of complication, like something as simple as this. Any memory operation that manipulates strings, for instance, it gets translated into very complex code with loops, low-level loops that access arrays. So it's a pretty hard problem to document all of those, whereas storage is also a hard problem, but mostly solved. So the main idea here is we just had a paper a couple of months ago at ICSI for storage modeling, and it had tremendous success. So for recovering the data structures that are actually sitting on the blockchain, we do very, very well. So if I am to summarize the status of decompilation for EVM smart contracts, I would say for control flow, which is everything, all the arguments that we've discussed so far, I would say we have a 99% solution. I mean, there's still room for improvement. Someone may want to build a decompiler based on symbolic execution, for instance, or based on LLMs people are trying to do. No algorithmic core at all. You just dump the disassembled on an LLM and see how well it can do. So there could be room for improvement here, but this is very close to perfect. For function recovery, we are good enough. Memory modeling, nobody's good enough. Nobody can get right now over 90% fidelity in recovering array operations from all the low-level code, for instance, from all the low-level manipulation of the transient memory. For storage modeling, we've done tremendously well. So we recover all of that very, very well. So overall, my point is that decompilation by static analysis is a huge win. It can be a huge win, especially in settings like this that require completeness, but also significant precision. And of course, the general message is that formulating a static analysis as a standard core that's parameterizable by different kinds of context, that has been a huge win, but that's also the message of much of my research work of the past 20 years. That's part of what I've done also for Java and for LLVM, especially for Java. Most of my analysis algorithms have been based on that second thing. A common core, and then have a couple of key points, key constructors, and you change those and you get a very different algorithm because you modify the shape of the context, either the depth of the context, but also how it gets updated at interesting points. And that's about it. So there are several publications, but you can all Google for them, so you don't really care that much about the specific publications. But I think this is the right conclusion to leave you with and take questions.
So we do have some time for questions. Please go ahead.
Hello, thank you for the talk. It was really interesting. So you talked about the design of other EVM-based decompilers, but have you considered more typical, like just binary decompilers like Ghidra, Binary Ninja, IDA Pro, and contrast the designs with what you've done here?
Well, I have right now, as of very, very recently, I have a joint project with Gang Tan of Penn State, who have done a pointer analysis on the output of an x86 decompiler. So I've just started hacking at their code base as well. So they're doing a great job. Let's just say, without being too specific, the tools you mentioned, IDA Pro, Ghidra, et cetera, they're not that good. They're pattern-based. They're not doing very deep analysis. I think we can do a lot better in that space. So if there's If there's business promise, we may take it on, but it sounds like a very niche space, and there may not be tremendous business promise enough to branch out to that. But in technical terms, I would say I will know a lot more in a year or so to tell you, because we are actively working on this. But they're not as good decompilers as what we've seen here. So it's quite possible that the very same techniques can be applied to x86 decompilation very fruitfully. But that's my speculation. I don't have evidence right now.
Hey, great talk. Do you have to worry yet about adversarial contracts that are designed to defeat your context sensitivity policies?
Not so far. So far, we have not. And also, it kind of makes sense that people will not go to great lengths to defeat specifically our policies. People want to get a little bit of a competitive advantage, but they will not get too much, because let's say we're talking about a hack, right? Hack contract, for instance. You have a hack contract, typically you will deploy it the last minute before you perform an attack. So you've performed your attack. You haven't lost that much by us reverse engineering it. But the short answer is, so far, we have not had too much of that. There is one technique that we don't do great on, which is a technique that doesn't actually have the jumps, the destinations of jumps statically at all in the code. It provides them as call data. When a transaction starts, it gives you a stack of where to jump to, which is perfectly possible. So there, we need to combine some dynamic information with static information. But yes, there are things that can defeat our algorithms, so to speak. If you take some static information and you make it dynamic, for instance, there are always countermeasures to those. In practice, this is not such a huge deal. Like, for the vast majority, we have a very, very good tool.
Hi. So did you have to adapt? My question is about data log solver. You did not mention specifically if you can use any data log solver, or you have to adapt precisely some algorithms inside.
I mean, there's only one. There's only one data log solver.
Yours.
If you're not publishing papers about the solver, you're using Souffle. There's nothing as mature as Souffle.
And
I mean, there are good solvers. There are many good solvers that come out, but they're more research products. And there's nothing that Souffle is really missing.
But then my question is, did you need to add new features to this solver for this specific problem, or not?
Yeah, that's a very good question. So did we need to add new features? In a limited way, yes. So for instance, we added some persistent data structures. You do this with functors. So we write C++ functors that Souffle is calling. So it's an external function interface. It's a foreign function interface, pretty much, that Souffle offers. And some data structures we implement in C++. But for very limited things, like in the path-sensitive algorithm, for instance, for very quick manipulation of long paths, of long sequences of basic blocks, we use that. So we do have some custom data structures, but for the most part, we didn't need to do any major surgery. And of course, we have functors. We have extended Souffle with 256-bit arithmetic, which it didn't have natively. So anything that has to do with EVM quantities, we've implemented ourselves in C++, and they're just external calls for the data log solver.
OK, we will take the last question from Elizabeth.
Thank you. So it seems that the bytecode is very abstract. You lose a lot of information, and there's complications with the dynamic jump locations. Are there implications in the testing literature for fuzzers that are measuring how good their tools are based on number of branches covered?
But dynamically, the branches are very clear dynamically. So for fuzzers, this is not a complication, because a fuzzer does execution. So it actually does find all the branches. Oh, If you take the if you say that a jump I, a conditional jump, has only 2 next paths, it only has 2 outputs, which is statically known. Then you measure how many you covered, whether you covered both, then you can get actually extremely precise branch coverage. So it's not a complication for fuzzers as much as it is a complication for static analyzers, either based on context-sensitive static analysis or even symbolic execution. That would be a complication. But for fuzzers, that's a good point, but it's actually it's well recognizable in the bytecode how many branches there are, because the jump I, there's no switch with an unbounded number of jumps. It's only jump I. Either you take it or you don't. So you can know the branches.
Okay, so we are out of time. Let's thank the speaker now.